What is the meaning of a limit, if not to be tested? Humanity is a story of breached barriers and shattered horizons. We were born to the earth, yet we learned to swim the seas. We were bound by gravity, yet we broke its hold and touched the moon. Every frontier we have ever faced, from the deepest ocean trench to the silent, airless void, has eventually yielded to our relentless curiosity. But there is one barrier that seems different. One cosmic law that stands not as a challenge, but as an absolute unyielding decree written into the very fabric of existence. It is a wall built of pure light. For more than a century, our understanding of the universe has been shaped by a single, elegant, and terrifyingly restrictive idea: nothing, absolutely nothing, can travel faster than light in a vacuum. It is not merely a technological hurdle we have yet to overcome, like building a better engine or a stronger ship. It is, according to Albert Einstein's theory of special relativity, a fundamental property of spacetime itself. 299,792,458 meters per second. This isn't just a speed, it is the speed, the ultimate velocity, the universe's final word on how fast anything with mass is allowed to move through the cosmos. Imagine for a moment you are at the helm of a futuristic starship, its engines capable of generating forces beyond our wildest dreams. You begin to accelerate, pushing forward into the black. As your velocity increases, something strange begins to happen. From your perspective inside the ship, everything feels normal, but to an observer watching you streak by, time aboard your vessel begins to slow down, its river-like flow becoming thick and sluggish. The ship itself, in the direction of its motion, appears to shrink, compressed by the sheer strain of its impossible journey. These are not illusions. They are the real, measurable consequences of approaching the cosmic speed limit. The most profound change, however, is happening to your ship's mass. According to the most famous equation in history, E equals mc squared. Energy and mass are two sides of the same coin. To make something move faster, you must give it more kinetic energy. But as you approach the speed of light, that energy begins to manifest in a peculiar way. It doesn't just increase your speed, it begins to increase your mass. Your ship becomes heavier and heavier. At 90% of light speed, your mass has more than doubled. At 99%, it has inflated by a factor of 7. At 99.999%, your once sleek vessel now possesses the inertia of a small asteroid. The energy required for each new increment of speed becomes astronomical, then infinite. To reach the speed of light, to push your ship over that final infinitesimal threshold, you would need an infinite amount of energy to move your now infinitely massive ship. The universe demands a price that cannot be paid. The wall of light holds. This is not merely a theory, it is one of the most rigorously tested and confirmed principles in all of science. In the colossal underground rings of particle accelerators, we have pushed subatomic particles to the very brink of this limit, spending vast amounts of energy to nudge them just a fraction of a percent closer to that ultimate velocity. And every single time, without exception, the universe has enforced its law. The math is unforgiving. The experiments are conclusive. The speed of light is the absolute governor on the cosmic engine, the boundary that separates the here and now from the there and then. For a species that dreams of star-spanning civilizations, this is a devastating realization. The nearest star system, Proxima Centauri, is over 4 light-years away. A journey at our current fastest speeds would take tens of thousands of years. Even if we could build a ship that travels at 99% of the speed of light, the journey would still take more than 4 years for those of us left waiting on Earth. The Milky Way galaxy, our home, is 100,000 light-years across. To traverse it, to truly become a galactic species, would take longer than our species has existed. The cosmos becomes a vast, lonely ocean, its islands of light separated by gulfs of time so immense they mock our brief lifespans. We appear to be prisoners in our own stellar neighborhood, our grandest ambitions checked by an immutable law of physics. Science fiction, of course, has always refused to accept this verdict. It gave us warp drives that bend space-time like a sheet of paper. It imagined hyperspace, a separate dimension where the rules are different. It dreamed of stargates and wormholes, cosmic shortcuts that stitch distant points of the universe together. These are wonderful, inspiring fantasies, escape clauses for our imagination. But are they anything more? Physicists themselves, the very guardians of relativity's laws, have cautiously explored these concepts. They have drafted complex equations describing how a wormhole might in theory be stabilized by exotic matter with negative energy. They have sketched out the mathematical architecture for a warp bubble, a pocket of space-time that could propel a ship without it ever locally breaking the light-speed barrier. These ideas, while mathematically plausible, remain far beyond any conceivable technology requiring conditions and materials that may not even exist. They are beautiful equations about impossible machines. They represent attempts to find a crack in the wall, a cleverly hidden door in the cosmic prison. But what if we've been asking the wrong question all along? What if the goal isn't to find a way to times break times the speed of light? What if the secret is to accept that the universe has two sets of rules for two entirely different kinds of existence? What if there are things in the cosmos that were simply born on the other side? This is where our journey truly begins, in a realm of pure theory, where mathematics becomes a kind of prophecy. It is a story that started not in an observatory but as a ghost haunting the elegant architecture of Einstein's own equations. When physicists explored the mathematical implications of relativity, they found something strange. A shadow solution, a mirror image of our own reality lurking just out of sight. The equations that so perfectly describe our universe, the one where energy makes you heavier as you go faster, also allowed for a bizarre inverted possibility. They described a class of particle that would possess properties so counterintuitive they seem to defy all logic. For these particles, the speed of light is not a maximum limit but a times, minimum times 1. They can never, ever travel times, slower times than light. They are born faster than light, they live faster than light, and they will die faster than light. To slow one down to the speed of light would require, just as in our own universe, an infinite amount of energy. The light barrier is a two-way wall. We are trapped on one side, and they are trapped on the other. In the 1960 seconds, physicist Gerald Feinberg gave these theoretical phantoms a name drawn from the Greek word tachys, meaning swift. He called them tachyons. The concept is a radical departure from everything we know. All the matter we have ever seen or touched, from the dust on our hands to the fiery cores of distant stars, is made of what we now call tachyons, or slow particles. They are the stuff of our reality. Then there are luxons, like the photon particles of light itself, which are massless and travel times at times the cosmic speed limit precisely. Tachyons would form a third unseen family of existence, a superluminal shadow world forever beyond our direct grasp. To make sense of this, we have to confront the strangest property of all, the source of their impossible speed, their mass. In our universe, mass is a positive real number. It creates gravity. It provides inertia. It is the very definition of substance. A tachyon, according to the mathematics, would have to possess what can only be described as imaginary mass. This isn't to say it's make-believe. In physics and engineering, imaginary numbers are powerful tools used to describe real phenomena, like alternating currents or quantum wave functions. Here, the term signifies a property fundamentally different from, and in a sense perpendicular to, the mass we are familiar with. It is as if reality has a second dimension of substance that we have never been able to perceive. The consequences of this imaginary mass are profoundly weird. Consider our starship again. As we pour energy into its engines, it accelerates, getting closer and closer to the speed of light. For a tachyon, the opposite is true. As a tachyon loses energy, it speeds up. A tachyon with very little energy would flash across the cosmos at almost infinite velocity. If you were to add times energy to it to push it forward, it would paradoxically slow down, its speed decreasing as it approached the light barrier from the other side. Its lowest possible energy state is infinite speed. Its highest energy state is the speed of light. It is a universe turned completely inside out, a place where braking is accelerating and effort creates drag. For decades, tachyons were treated largely as a mathematical curiosity, a quirk in the equations that most physicists assumed must be forbidden by some yet unknown principle. They were a sign that the theory was being pushed too far, a kind of mathematical warning sign pointing to a breakdown in our understanding. no one had ever detected one. There was no evidence that this shadow realm of faster-than-light particles was anything more than a fiction spun from abstract symbols. But science is littered with mathematical ghosts that later materialized as real-world discoveries. The positron, the antimatter twin of the electron, was first discovered as an odd negative energy solution in Paul Dirac's equations before it was ever observed in a laboratory. The neutrino, a ghostly particle that can pass through planets as if they were empty space, was first proposed to balance a theoretical energy budget before it was finally captured. Could tachyons be another such case? Awaiting discovery, waiting to fundamentally rewrite our map of reality. The search for them is one of the most tantalizing and frustrating quests in modern physics. How do you even look for something that might exist outside of our conventional notions of space and time? How do you build a net to catch a ghost? Some have looked for their signature in the cosmic microwave background, the faint afterglow of the Big Bang, searching for telltale anomalies. Others have scrutinized high-energy cosmic rays bombarding our atmosphere, hoping to catch a fleeting glimpse of a particle behaving in a way that no ordinary matter should. So far, the universe has kept its secrets. We have found no definitive proof that tachyons are real, but their possibility continues to haunt us because their existence would not just be a fascinating addition to the particle zoo. It would shatter our most deeply held beliefs about the universe, forcing us to confront a possibility far stranger than just faster-than-light travel. It would force us to question the sacred arrow of time itself. Imagine you could build a tachyon transmitter, a device that could encode a message onto a beam of these particles and fire it at a distant receiver. Because the tachyon is moving faster than light, the message would arrive at its destination before a beam of light sent at the same instant ever could. This seems straightforward enough, but this is where relativity's true strangeness rears its head. Einstein showed that simultaneity is not absolute. Observers moving at different speeds can disagree on the order of events. For one observer, your tachyon message arrives after it was sent. But for another observer moving at high velocity relative to you, the mind-bending logic of space-time transformation equations predicts something utterly impossible. They would see the message being received times before times it was ever transmitted. The effect would precede the cause. A reply could be sent back to you that arrives before you've even asked the question. You could receive tomorrow's winning lottery numbers today. You could learn of a catastrophe and send a warning back in time to prevent it, creating a paradox that threatens to unravel the logical consistency of the entire universe. This is the true terror and the ultimate allure of the tachyon. It isn't just a particle, it is a potential key to causality itself. The chain of cause and effect, the unwavering progression from past to present to future, is the bedrock of our sanity, the fundamental grammar of our reality. If tachyons exist and if they can be harnessed, then that grammar is broken. The story of the universe would no longer be a book read from front to back, but a scrambled collection of pages that can be read in any order. So we are left standing before two towering possibilities. Either tachyons do not exist, and the universe is protected from such paradoxes by a fundamental law we have yet to fully grasp, or they times do times exist, and the nature of time and causality is something far more complex, far more mysterious, and perhaps even more terrifying than we have ever dared to imagine. The search for this impossible particle is therefore a search for ourselves, for the ultimate rules that govern our place in the cosmos. Are we bound to the slow, inexorable march of time, or is there another way to exist? A faster, stranger path, hidden just beyond the shimmering wall of light? What if the universe, in its very code, has a single absolute command, a law etched not in stone, but into the fabric of reality itself? A law that simply says, no. A universal prohibition against the one thing our species has always craved more than anything else, true unbounded speed. The power to outrun a sunbeam, to cross the gulf between worlds in a blink, to send a message and receive its reply before a single breath is taken. For all our dreams of the stars, for all our boundless ambition, we have always found ourselves staring at a wall. A wall built not of matter but of mathematics. A barrier woven from the very nature of light and time. To understand this wall, we must travel back to the dawn of the 20th century. to a quiet patent office in Bern, Switzerland, where a young clerk, a man whose genius would soon redefine our cosmic address, was wrestling with a profound paradox concerning the speed of light. His name was Albert Einstein, and the revolution he was about to unleash was not merely a new theory, but an entirely new conception of the universe. His 1,905 papers on special relativity were not a discovery in the traditional sense. They were an epiphany, a revelation about the geometry of existence. He proposed that space and time were not the separate, rigid entities we experience them as. They were not a fixed stage upon which the events of the universe played out. Instead, they were inextricably linked, woven together into a single dynamic continuum, space-time. And through this four-dimensional fabric there was a single immutable speed limit, a velocity so fundamental, so absolute, that the universe itself conspires to protect it. We call this constant Sir, the speed of light in a vacuum, approximately 186,282 miles per second, a number so immense it feels abstract, yet it is the most concrete law we know. It is the universe's ultimate gear, the highest velocity anything can ever hope to achieve. But the true strangeness, the deep world-altering mystery of c, is not just its value, but its unwavering consistency. Imagine you are on a train moving at 100 miles per hour and you throw a ball forward at 20 miles per hour. To someone standing on the platform, the ball appears to be moving at 120. Simple, intuitive addition, but light refuses to play by these rules. If you are on a spaceship traveling at 99% of the speed of light and you turn on a flashlight pointing it forward, that beam of light does not travel at 199% of car. To you on the ship, and to someone watching from a distant planet, that beam of light moves at exactly the same speed. The universe literally warps space and stretches time to ensure this one rule is never, ever broken. The speed of light is not just a speed, it is the source code of physical law, the cosmic anchor around which all of motion and causality pivots. It is the ultimate authority. For anything made of the familiar matter that constitutes you, me, the planets and the stars, this law presents an insurmountable barrier. The reason lies within Einstein's most famous yet often misunderstood equation, E equals mc squared. We see it and think of atomic power, of the immense energy locked within the heart of matter, but its deeper meaning is a statement of equivalence. Energy has mass, and mass is a form of concentrated energy. They are two faces of the same fundamental coin. This is not just a philosophical concept. It has profound physical consequences for motion. As you accelerate an object, you pump kinetic energy into it. According to Einstein, that added energy must also contribute to the object's mass. So the faster an object with mass moves, the more massive it becomes. At the slow, ponderous speeds of our everyday lives, this effect is infinitesimal, utterly undetectable. A cruising jetliner is heavier than a parked one, but only by a weight less than that of an amoeba. But as you approach the speed of light, the consequences become catastrophic. Imagine you are trying to push a cosmic freight train. At 10% of light speed, it's already noticeably heavier. You need more and more fuel, more and more thrust just to gain the next increment of speed. At 50% of light speed, its mass has increased significantly. At 80, 90, 99%, the train's inertia begins to skyrocket. You are no longer just fighting to make it go faster. You are fighting its very substance, which is bloating, swelling, becoming more stubborn with every meter per second. The universe itself is resisting your efforts, converting the furious energy of your engines not purely into speed, but into sheer ponderous mass. It's like trying to run through water that thickens into concrete the faster you move. Now push it to the very edge. 99.999% of the speed of light. The object's mass has ballooned to staggering proportions, its inertia approaching the infinite. To add that last tiny fraction of a percentage point of speed to finally touch the luminous finish line of COM would require an infinite amount of energy. You would need to convert the entire energy of the known universe into thrust to nudge that final impossible inch forward. This is not a technological challenge to be overcome with better engines or more exotic fuels. It is a fundamental law of space-time, a perfect prison. an elegant, inescapable cage of cosmic law defining the boundaries of our physical existence. For anything with what we call real mass, the speed of light is not a goal. It is an asymptote, a horizon you can forever approach but never ever reach. For decades, this was the end of the story. A beautiful, complete, but ultimately confining theory. The universe was divided into two classes of entities, those with mass called tachyons or bradyons, doomed to forever travel slower than light, and those without mass like photons, the particles of light themselves, which have no choice but to travel exactly at times the speed of light always. There was no in-between, and certainly no beyond. The rule was absolute. The door was locked. But what if we were trying to open the door the wrong way? What if we have been looking at the bars and not the space between them? The equations of special relativity are unforgiving. They present an infinite energy wall at speed. But that wall works both ways. It stops us from accelerating times up to times the speed of light. What if something didn't need to accelerate to it? What if something was simply born on the other side? This was the revolutionary question that began to percolate in the minds of theoretical physicists. A question that treated Einstein's wall not as a boundary to the universe, but merely as a border between two vastly different territories. In 1967, physicist Gerald Feinberg at Columbia University was exploring the mathematics of relativity, pushing the equations into this forbidden, seemingly nonsensical territory beyond. He was not trying to break physics. He was simply following the logic of the mathematics wherever it might lead, no matter how strange the destination. And it led him to a ghost in the machine. A theoretical possibility for a new class of particle, one that could exist in perfect harmony with special relativity, so long as it obeyed one bizarre mind-bending condition. It could never ever travel slower times than the speed of light. Feinberg gave these hypothetical particles a name derived from the Greek word tachys, meaning swift. He called them tachyons. The very concept seems like a flagrant violation of everything we've just established. A particle that travels faster than light, doesn't that shatter the foundations of relativity? The answer, astonishingly, is no. And the reason why reveals a deeper, more beautifully symmetric structure to the universe than we ever imagined. The key is that infamous equation E equals mc squared, or rather its more complete relativistic form. When physicists plugged a velocity greater than c into this equation, a mathematical nightmare appeared in the results. The term for mass was forced to become the square root of a negative number. In school, we are taught that you cannot take the square root of a negative number. There is no real number that when multiplied by itself gives a negative result. But in the higher realms of mathematics and physics, these numbers are not only possible, they are essential. They are called imaginary numbers, and this is the secret to the tachyon's existence. The word imaginary is perhaps the most unfortunate misnomer in all of science. It does not mean make-believe fictional or unreal. An imaginary number is just as valid and consistent as a real one. Think of all the real numbers 1, -5 pi as points on an infinite horizontal line. Imaginary numbers simply open up a new dimension. They create a vertical axis, turning the one-dimensional number line into a two-dimensional plane. They represent a kind of possibility that real numbers alone cannot describe. And according to the mathematics of relativity, for a particle to exist permanently in the superluminal, faster-than-light realm, it must possess this quality. It must have an imaginary mass. This single, seemingly absurd property changes everything. It flips the entire rulebook of motion on its head. For us, in our world of real mass, energy is the price of speed. The more energy we pour into a particle, the faster it goes, approaching the light barrier from below. For a tachyon, the opposite would be true. A tachyon with near infinite energy would be traveling at its slowest possible speed, just barely faster than the speed of light. It would be lumbering along the light barrier from the other side. To make a tachyon go faster, you would not add energy, you would have to take it away. A tachyon that has lost almost all of its energy would be moving at nearly infinite speed, capable of traversing the entire galaxy in less than an instant. Think about the sheer paradoxical beauty of this. The speed of light is not just a ceiling for our universe. It is also a floor for the tachyonic realm. The infinite energy barrier that prevents our ships from reaching Ka is the very same barrier that prevents a tachyon from ever slowing down enough to enter our world. We are prisoners of slowness. They are prisoners of speed. Two distinct universes, two families of particles, tachyons and tachyons, occupying the same space-time, but forever separated by an impenetrable luminous wall. They are a potential dark mirror to our own reality. Where we gain mass with speed, they would lose it. Where we require infinite energy to reach the limit, they require infinite energy to slow down to it. They do not break the laws of relativity. They fulfill them in a way we never expected. They are the other side of the equation, the missing reflection. A shadow universe governed by a set of inverted physical principles, whose existence is not only permitted by our best physical theories, but in some sense demanded by their elegant symmetry. We are left then standing at the edge of a precipice. On one side, the solid familiar ground of our sublight existence governed by the clear and unyielding laws discovered by Einstein. Everything we can touch, see and measure lives here. On the other side, across a chasm of infinite energy, lies a hypothetical realm, a world of ethereal particles born in motion, for whom faster-than-light travel is not a dream but an inescapable condition of their being. These are not rogue particles violating cosmic law. They are the law's most exotic and fascinating children. If they exist, they populate a universe that is profoundly strange, one where our most fundamental intuitions about existence are turned inside out. But accepting their theoretical possibility is only the first step into this shadow world, for if these ghostly particles do streak unseen through our cosmos, their most unsettling property is not their unimaginable speed. It is what that speed would do to the most sacred principle of our reality, the unyielding forward arrow of time itself. And so if the cosmic speed limit stands as an immutable, insurmountable barrier, a wall of pure light that all of our known reality is forbidden to cross, a question naturally arises from the deepest wells of human curiosity. What, if anything, lies on the other side? For decades after Einstein, this was a question relegated to fantasy, a nonsensical inquiry like asking what is north of the North Pole. The equations seemed to build the wall brick by mathematical brick with the mortar of infinite energy required for any object with mass to reach it. The case, it appeared, was closed. But within the elegant architecture of those very same equations, a strange, almost imperceptible backdoor had been left ajar. It was a solution that most physicists had dismissed as a mathematical ghost, a phantom born of taking a square root of a negative number, an answer that our physical intuition told us must be meaningless. After all, our universe is a place of substance, of positive mass and real energy. It is a realm of concrete things, not the spectral echoes of impossible arithmetic. Yet mathematics often possesses a strange prescience predicting realities we have yet to discover, from black holes to antimatter. Could this mathematical spectre be more than just a ghost in the machine? Could it be a signpost pointing to an entirely different class of existence, a cosmic underbelly governed by rules so alien they seem to defy logic itself? In the whirlwind of the 1,960 seconds, a time of radical new ideas in every field of human endeavor, a young, audacious physicist at Columbia University decided to take this ghost seriously. His name was Gerald Feinberg, and he possessed the intellectual courage not just to peek through that mathematical backdoor, but to throw it wide open. He wasn't trying to break relativity. He was trying to understand its fullest implications, to follow the rigorous logic of its equations wherever they might lead, no matter how bizarre the destination. Feinberg looked at the Lorentz factor, the very heart of special relativity, the mathematical engine that dictates how time dilates and length contracts. He saw, as everyone had, the singularity at the speed of light, the point of infinity. But he also saw that if a particle were to somehow always times exist on the other side, if it were born into existence already moving faster than light, the equations didn't break down. Instead, they transformed into something profoundly strange, something self-consistent, a looking-glass version of our own universe. He gave this hypothetical particle a name derived from the Greek word for swift. He called it the tachyon. With this single act of naming, Feinberg gave substance to a shadow, initiating a theoretical exploration that would thrill and terrify physicists for generations. He had dared to imagine a particle for which the speed of light was not a goal to be reached, but a fundamental times lower times limit, a floor it could never drop below. For us, for every atom in your body and every star in the sky, light speed is the ultimate ceiling. For a tachyon, it would be the ultimate floor. We live in a world of tachyons, the slow particles forever bound beneath light speed. Feinberg proposed a second family of existence, the tachyons forever exiled to the realm times beyond times it. And in between, like a river of fire separating two alien continents, was the speed of light itself, populated only by massless photons, the lonely couriers permitted to travel the boundary but never truly belong to either side. This was a universe suddenly grander, more symmetric, and infinitely stranger. The elegance of the idea was intoxicating. It suggested that our perception of the cosmos was fundamentally incomplete, that we were living in only one wing of a much larger, more mysterious mansion. The walls of our reality, which had seemed so solid, were perhaps only semi-permeable, and through them the whispers of a faster reality were beginning to leak. To exist in this faster-than-light realm, a tachyon would need to possess properties that shatter our most basic intuitive understanding of the physical world. The first and most jarring of these is its mass. As an object with ordinary positive mass approaches the speed of light, its relativistic mass increases, demanding more and more energy for each tiny gain in speed, until at light speed, its mass and the required energy both become infinite. This is the essence of the light barrier. So how does a tachyon overcome this? The mathematics offered a solution that was both perfectly logical and deeply unsettling. For a tachyon, the term for mass inside the square root of the Lorentz equation becomes negative. The result is what mathematicians call an imaginary number. A tachyon, therefore, must have imaginary mass. What does that even mean? How can something possess a quality that seems by its very name unreal? It's a concept that forces us to detach from our physical experience of mass as heft or substance. Imaginary mass is not make-believe mass. It is a precise mathematical attribute. Think of it not as a substance, but as a description of a relationship, a tag that tells the universe how this particle must behave with respect to the light barrier, where positive mass acts like a cosmic anchor, tethering an object to the slow side of reality and making it infinitely difficult to reach the speed of light. Imaginary mass acts as a form of cosmic buoyancy. It is an anti-anchor, fundamentally repelling the particle from the light barrier, forbidding it from ever slowing down times to times the speed of light. Just as it would take infinite energy for us to reach the light barrier from below, it would take an infinite amount of energy for a tachyon to slow down and reach it from above. The tachyon is locked out of our world just as we are locked out of its. This property, this phantom mass, is the very key to its FTL existence. It is the universe's way of maintaining two separate self-consistent regimes of reality. And yet, while its mass is an imaginary quantity, its energy and momentum are not. They are real, measurable, and interact with the universe in their own unique way. A tachyon would be a genuine physical entity, a packet of real energy, but one constructed from a blueprint that feels utterly alien to our own. It's a ghost in the shell of reality, a particle whose very foundation is a number we invented to solve problems with no real-world solution, only to find that the universe may have been using that number all along to build a hidden layer of existence right alongside our own. The sheer philosophical weight of this is staggering. It suggests that the fundamental constants and properties we hold so dear might just be local bylaws, applicable only to our corner of creation, and that a whole other set of rules governs the universe's swift, unseen inhabitants. The universe, it seemed, was not just stranger than we imagine, it was stranger than we can times imagine. This foundational weirdness of imaginary mass gives birth to a second, even more mind-bending paradox, one that completely inverts our understanding of energy and motion. In our world, the relationship is simple, intuitive, and absolute. To make something go faster, you must give it more energy. A thrown baseball has more energy than one at rest. A speeding rocket burns colossal amounts of fuel, converting chemical energy into kinetic energy. More speed requires more energy. This is the bedrock of physics. From celestial mechanics to particle accelerators, tachyons would demolish this bedrock. For a particle born on the other side of the light barrier, this relationship is flipped on its head. As a tachyon speeds up its energy, time decreases, asterisk. As it slows down, approaching its lower limit of the speed of light, its energy times increases, asterisk. Let that sink in for a moment. Imagine a car that you had to drain fuel from to make it accelerate. Picture a sprinter becoming less tired the faster they ran. This is the bizarre, inverted world of the tachyon. At its slowest possible speed, the speed of light, a tachyon's energy would be infinite, an impossible state it can never truly reach, just as we can't from our side. But as it accelerates away from that barrier, moving faster and faster into the FTL realm, its energy continues to drop relentlessly, shedding its vitality with every increase in velocity. What happens if it keeps accelerating? Where does this inverted logic lead? It leads to the ultimate paradox of motion. As a tachyon approaches infinite speed, its energy approaches zero. A tachyon moving at an infinite velocity capable of being everywhere in the universe at once would have no energy at all. It would be a state of pure instantaneous motion, utterly without substance or impact. A silent, instantaneous ghost flitting across the entire cosmic stage in no time at all. This behavior is so profoundly counterintuitive that it challenges our definition of existence. In our universe, energy is what makes things happen. Energy is the currency of change, of interaction, of being. A particle with zero energy is for all intents and purposes a particle that isn't there. And yet, for the tachyon, this state of non-energy is its ultimate destination, the result of achieving the highest possible speed. This means that the most common state for tachyons, the lowest energy state they would naturally seek, is to be moving at infinite speed. Perhaps the universe is already filled with them, a sea of zero-energy ghosts crisscrossing the cosmos, instantaneously, utterly undetectable to our instruments, precisely because they have surrendered all their energy to achieve the ultimate speed. They could form a kind of cosmic nervous system, a network of instantaneous connections underpinning the very fabric of space-time, yet completely invisible. Feinberg's theoretical creation was becoming more and more phantasmagorical with each new revelation. It was a particle that existed in a state of perpetual paradox, an entity for which slowing down was an effort, and speeding up was a form of release, a journey toward a state of energetic nothingness. The thrill of this theoretical frontier was undeniable, a new physics ripe with possibility. But as physicists pushed the implications of these ideas even further, they stumbled upon a consequence so profound, so utterly devastating to our understanding of reality, that it threatened to collapse the entire theoretical edifice. The ghost in the machine was about to reveal a truly terrifying face. It began with a simple question. If a tachyon can travel faster than light, what does that mean for the concept of simultaneity? Einstein taught us that there is no universal now. Two observers moving relative to each other will disagree on the precise order of distant events. An event that you see happen first, another observer flying past you might see happen second. For all sublight phenomena, this disagreement is academic. While the sequence might appear to shift, cause and effect are always preserved. No one in any frame of reference will ever see an effect happen before its cause. A bullet will never arrive before the gun is fired. A ripple will never appear before the stone hits the water. This is the principle of causality, the most fundamental law of the cosmos. It is the ultimate if-then statement of reality, the chain of logic that makes the universe comprehensible. Cause precedes effect, always. This isn't just a rule of physics. It is the rule that allows physics to exist. Without it, the universe would descend into an incoherent madness of uncaused effects and ineffective causes. A world without causality is not a world at all. It is a nightmare. And this is the nightmare that the tachyon unleashes. Because a tachyon moves faster than light, it can, from the perspective of certain observers, arrive at its destination times, before times it leaves its source. Let's build a thought experiment, a so-called achionic anti-telephone. Imagine we have a device that can send and receive tachyons. You are on Earth, and your colleague is in a spaceship receding from you at nearly the speed of light. You decide to send her a message using a pulse of tachyons. From your perspective, everything is normal. You encode your message, fire the tachyon beam, and it travels much faster than light to her ship. Because you send the message, effect, she receives it, time passes, all is well. But now, let's look at this exact same event from her reference frame, from her moving spaceship. Because of the strange geometry of space-time described by special relativity, her motion relative to you radically alters her perception of time and space. From her point of view, the sequence of events she observes can be reversed. She will see the tachyon pulse arrive at her ship first, then later she will see you on Earth sending it. For her, the effect has preceded the cause. She has received a message from your future. This is already deeply troubling, a crack in the foundation of reality. But the true paradox, the one that shatters logic itself, comes with the next step. What if she immediately sends a message back to you? She receives your message, which from her perspective has arrived from the future. She instantly fires her own tachyon beam back at you. Because you are also moving relative to her, this return signal can also travel backward in her time. The final result, you will receive her reply times before times you ever sent your original message. Imagine picking up the phone to make a call and hearing the other person's answer before you've even had a chance to ask the question. Imagine receiving a message from your future self, warning you not to send the very message that prompted the warning in the first place. What do you do if you follow the advice and don't send it? Then the warning itself could never have been created and sent back to you. But if you never receive the warning, what stops you from sending the message? This is the dreaded grandfather paradox wrapped in the language of theoretical physics. It is a closed loop of logic that annihilates itself, a snake eating its own tail until nothing is left. The existence of a particle that can carry information faster than light appears to lead directly to the breakdown of causality. It doesn't just challenge our physical theories, it challenges the very notion of a consistent past, present, and future. The elegant, symmetrical universe proposed by Feinberg with its two families of particles now contained the seeds of its own destruction. The tachyon was no longer just a clever mathematical possibility. It was a potential weapon aimed at the heart of space-time, a theoretical monster that could unravel the entire tapestry of history. The initial excitement among physicists began to curdle into a profound sense of dread. Had they uncovered a stunning new feature of reality, or had they simply followed a siren song of beautiful mathematics into an inescapable vortex of paradox? The question was no longer just, can tachyons exist? The question had become, how could the universe possibly allow them to? And so the celebration screeches to a halt. The exhilarating sprint into a faster-than-light future slams headfirst into a wall of absolute unyielding logic. For in the very same mathematics that gives birth to the tachyon, that grants it license to outrun the cosmos, there lurks a poison pill. A terrible secret is encoded into its very existence, a consequence so profound, so utterly subversive, that it threatens not just our theories of physics, but the bedrock of reason itself. This consequence has a name, one that physicists whisper with a mixture of fear and reverence: causality. The inviolable law that an effect can never precede its cause. It is the most fundamental rule of our shared existence, the silent metronome that orders our lives. A glass falls times, then times it shatters. A star is born times its light begins a long journey across the void. Every memory you possess, every action you take is predicated on this simple linear procession from past to present to future. It is the spine of reality, the sacred chain linking one moment to the next, ensuring the universe is a coherent story and not a mad jumble of disconnected events. Tachyons, in their glorious, impossible speed, do not merely bend this rule. They take that sacred chain, that spine of reality, and with chilling indifference they snap it in two. To understand how we must revisit that strange landscape of space-time we explored earlier, remember that for any two observers moving at different speeds, their measurements of time and space will differ. Their clocks will tick at different rates, their rulers will seem to shrink and stretch. Einstein's relativity weaves a universe where simultaneity is a local illusion. What appears to happen at the same time for you might happen in a different order for someone flying past in a starship. For everything moving slower than light, this temporal shuffling is tightly constrained. The universe has a built-in safety mechanism ensuring that no matter how fast you go, the order of cause and effect remains absolute for everyone. A gunshot will always precede the impact. But for a tachyon, this safety mechanism fails catastrophically. Because it moves faster than light, it can traverse a distance so great, so quickly, that it outpaces the very information of its own departure. This creates a bizarre loophole in relativity. There will always be a frame of reference, a certain velocity an observer could travel at, from which the tachyon would not just appear to be moving incredibly fast, it would appear to be moving backward in time. Its arrival would be witnessed before its departure. The effect would be observed before its cause was ever initiated. This isn't just a quirky mathematical artifact, it is the key that unlocks Pandora's box. If we could harness these particles, if we could build a device to send and receive them, we would have created something more potent than a starship, more dangerous than any weapon. We would have built an anti-telephone, a device for talking to the past. Imagine two scientists stationed light years apart. Let's call them Alice and Bob. Alice has built a tachyonic transmitter and Bob a receiver. From our stationary perspective, they plan a simple experiment. On Monday at noon, Alice will send a tachyon pulse across the stars to Bob. Because it travels faster than light, the pulse arrives at Bob's station almost instantly, let's say Monday at 12:01 p.m. So far so good, a near instantaneous message. But now, let's introduce a third player, an astronaut named Chloe, flying in a starship on a trajectory between Alice and Bob, moving at a significant fraction of the speed of light relative to them. From Chloe's perspective, the strange magic of relativity begins to warp the sequence of events. Due to her velocity, her perception of time and space is different. When she observes the experiment, she sees Bob's receiver flash at 12:01 p.m. on Monday, just as we did. But when she looks back towards Alice's transmitter, she sees something impossible. She sees Alice Times press the button to send the signal times at 12:02 p.m. From her moving viewpoint, the tachyon arrived at Bob's station a full minute times before times it was ever sent from Alice's. The effect has unambiguously preceded the cause. The scientific community, upon first grappling with this, was staggered. The thought experiment conceived by physicist Richard Tolman decades ago wasn't a flaw in logic. It was a direct, unavoidable result of combining the known laws of relativity with the hypothetical properties of a faster-than-light particle. The universe, it seemed, had a ghost in its machine. The implications were not merely philosophical, they were terrifyingly practical. What if Bob, upon receiving the message at 12:01, immediately sends a conventional light-speed message back to Alice, telling her the experiment was a success? That message, travelling at the cosmic speed limit, might reach Alice at 12:01 and 30 seconds. She would then receive confirmation of a successful transmission 30 seconds times before times. She actually decides to transmit it. What does she do? She now possesses knowledge of the future. She knows that in 30 seconds she is going to press the button. But what if she chooses not to? What if, armed with this foreknowledge, she simply walks away from the console? Her decision, her act of free will, now directly contradicts the message she has already received. The event that caused Bob to send his confirmation message, her tachyonic pulse, now never happens. So how could Bob have sent his message in the first place? The entire chain of events evaporates into a fog of pure contradiction. The past has been changed by a future that now cannot exist. Reality has just divided by zero. This is the Tolman paradox, the anti-telephone, and it is the gateway to an even deeper level of cosmic insanity. It demonstrates that tachyonic communication is not merely communication, it is temporal sabotage. It weaponizes information, turning it into a tool to rewrite history, creating logical loops that devour themselves. The past would no longer be a fixed, unchangeable country from which we came. It would become a fluctuating, unstable battleground, constantly being altered by messages from its own future. Every decision you ever made could be retroactively nullified. The outcome of a lottery, the result of a war, the birth of a child, all could be altered by a single bit of information sent hurtling back through the years. Our entire understanding of progress, of learning from mistakes and building upon the past, would become meaningless. How can you build a future on a foundation of sand that is constantly shifting beneath your feet? The universe would lose its memory. It would be a story with no fixed pages, endlessly rewriting itself into nonsense. This chilling prospect was for many physicists the end of the conversation. Tachyons, they argued, simply cannot exist. The paradox isn't a puzzle to be solved, it's a cosmic stop sign. It is the universe's way of telling us that the equations might permit such a thing, but the fundamental logic of existence forbids it. Nature, they claimed, must have a built-in censorship mechanism that prevents such causal violations. Perhaps generating and controlling a single tachyon is a fundamentally impossible engineering task, or perhaps their interactions with normal matter are governed by some yet undiscovered law that prevents them from ever carrying coherent information. For this camp, the beauty of the mathematics was irrelevant. It was a siren song luring physics towards a cliff of pure absurdity. Tachyons were relegated to the dustbin of elegant but failed ideas, a mathematical curiosity with no physical reality. But for another group of thinkers, this was not an end, but a profound and tantalizing beginning. They looked into this abyss of contradiction and saw not a barrier but a doorway. What if the paradox wasn't a sign that tachyons are impossible, but rather a sign that our understanding of time, causality, and information is tragically incomplete? What if the universe is far stranger, far more resilient than our simple, linear assumptions allow? This question forced science to the edge, compelling it to confront the most famous and unsettling of all temporal riddles, the grandfather paradox. The anti-telephone deals with the paradox of information. The grandfather paradox escalates the problem to the paradox of action. It takes the abstract threat and gives it a human, visceral form. The setup is gruesomely simple. You build a tachyonic time machine, not just a communicator, but a vessel capable of carrying matter back through the causal stream. You have a target, your own grandfather. You travel back to a time before he met your grandmother, before your own parent was ever conceived. You find him as a young man, and you kill him. Now the universe has to answer an impossible question. If your grandfather died as a young man, your parent was never born. If your parent was never born, you were never born. If you were never born, you could never have built the time machine. And if you never built the time machine, you could never have gone back to kill your grandfather. Who then was the killer? The universe is trapped in a vicious, unbreakable loop of self-negation. Your existence and your non-existence become simultaneously true and false. The act of murder prevents the murder from ever happening, which in turn allows the murder to happen, which in turn prevents it. It is a logical black hole from which no coherent reality can escape. This wasn't just a thought experiment for philosophers anymore. The potential existence of tachyons dragged this nightmarish scenario out of science fiction and dropped it squarely onto the desk of theoretical physics. It became a litmus test. Any theory that permits the grandfather paradox is by definition a broken theory. Therefore, if tachyons are to exist in our universe, there must be some profound hidden rule that prevents this outcome. Physics found itself in an extraordinary position. It was forced to become the defender of its own sanity, to search for a loophole in the paradox, a cosmic law that would allow for the river of time to be breached, without causing it to flood and destroy the entire landscape of reality. Two major battle lines were drawn in this high-stakes intellectual war. On one side were the champions of cosmic consistency. They proposed a radical yet elegant solution known as the Novikov self-consistency principle. This principle states that while time travel to the past might be possible, any action you take in the past was always times part of history. The universe, in its fundamental structure, forbids paradoxes from occurring. You can travel to the past, but you cannot change it. In this view, free will becomes a grand illusion when dealing with closed time-like curves. You can go back to confront your grandfather, but something will always prevent the murder. Perhaps you trip and fall at the last second. Perhaps your weapon misfires. Perhaps you have a change of heart, discovering he is not the person you thought he was. Or in a more sinister twist, perhaps your very presence in the past is the event that causes your grandparents to meet in the first place. You become an unwilling, unwitting agent of your own creation, your attempt to erase your own timeline, ironically becoming the very act that ensures it. The universe doesn't break, It simply and implacably ensures that its history is a single, self-consistent, unchangeable story. Any event that occurs is woven into the tapestry from the beginning. There are no alternate timelines, no rewritten histories, only one eternal looping and unbreakable narrative. This idea is both comforting and deeply unsettling. It saves reality from contradiction, but it does so at a tremendous cost. It suggests a form of cosmic determinism, a block universe where the past, present, and future are already written, fixed, and immutable. Your journey into the past is not an act of freedom, but the fulfillment of a destiny you never knew you had. Tachyons could exist, but their power to alter reality would be a mirage. They would allow you to witness the past, perhaps even participate in it, but never ever to change a single letter of its story. On the other side of the battlefield, a far more radical, far more mind-bending proposition was gaining ground. It came from the strange world of quantum mechanics, a realm already comfortable with probability, uncertainty, and observers splitting reality. This was the many worlds interpretation. This theory posits that the universe at every quantum decision point splits into multiple parallel universes, one for every possible outcome. Every choice you could have made, you did make in some other branch of reality. When applied to the grandfather paradox, this idea provides a spectacular escape route. When you travel back in time and kill your grandfather, you don't actually alter your own past. Instead, your arrival creates a new fork in the river of time, branching off a new parallel universe. In this new timeline, your grandfather is dead, and you will never be born there. But you, the time traveler, are now an orphan of causality, a refugee from a timeline that still exists completely unaffected back in the multiverse. You have succeeded in your mission, but you have not created a paradox. You have simply created a new tragic reality and stranded yourself within it. This solution preserves free will. You can make any choice you want in the past, but it does so by shattering the idea of a single coherent reality. It populates the cosmos with an infinite, ever-growing froth of parallel worlds, each with its own history, its own truth. The existence of tachyons in this view would be the key to unlocking this multiverse, turning them into vessels not for rewriting history, but for navigating the endless sea of alternate realities. It's a breathtaking, gargantuan vision, one that saves logic, but perhaps loses any sense of a shared singular existence. And so the scientific community found itself at a profound crossroads, a turning point forced upon it by a single hypothetical particle. Tachyons had become a cosmic mirror, reflecting back our deepest questions about the nature of being. Are we masters of our fate, or are we actors in a pre-written play? Is our reality singular and sacred, or is it just one leaf on an infinite tree? The paradoxes they create are not just intellectual games, they are fundamental challenges to our place in the cosmos. They force us to choose between a universe that is logical but deterministic and a universe that allows for freedom but is splintered into countless copies of itself. The question of whether tachyons exist is no longer just a question of physics. It has become a question of metaphysics. Before we can even continue the search for them in the depths of space or the wreckage of particle collisions, we must first confront the chaos they would unleash here in our understanding of the universe itself. Is there a third option, a path between the iron cage of determinism and the lonely infinity of the multiverse? Is there some hidden principle, some piece of the cosmic puzzle we are missing that would allow for faster than light travel without destroying the very meaning of time? The stakes could not be higher, for to solve the paradox of the tachyon is to solve the riddle of time itself, and so we find ourselves standing at the edge of a conceptual abyss. Having confronted the spectre of causality, the harrowing vision of a universe where effect can precede cause, where the future can rewrite the past, we are forced to ask a question that feels like a betrayal of our own curiosity. Is this where the search must end? Does the sheer sanity-preserving logic of a one-way arrow of time demand that we close the book on particles that travel faster than light? For many physicists, the paradox was a wall, an intellectual dead end so profound that it seemed to forbid any further inquiry. Yet the equations of relativity, those pristine mathematical poems written by Einstein, still whispered of the possibility. The mathematics did not forbid tachyons, it merely described their bizarre inverted world. For a select group of pioneers, the paradox was not a stop sign, but a challenge. It was a warning label on a door that they were now more determined than ever to unlock. If these phantoms did exist, then nature must have found a way, an elegant and subtle solution to protect its own integrity. The universe, they wagered, was cleverer than our paradoxes. And so, with the chilling implications of shattered causality still echoing in their minds, they turned away from the chalkboard and towards the laboratory. The time for pure thought was over. It was time to go hunting. The hunt for a tachyon is unlike any other pursuit in science. You are not searching for a thing so much as the fleeting signature of its impossible passage. How do you catch a ghost? How do you photograph a particle that arrives before it has left? The primary method, a strategy of profound cleverness, was to look for a very specific kind of light, a unique electromagnetic shockwave. We are familiar with the sonic boom created by a jet breaking the sound barrier. In a similar fashion, when a charged particle travels through a medium like water or air faster than the speed of light, times in that medium times, it emits a ghostly blue glow. This is Cherenkov radiation. A tachyon, however, would be a creature of an entirely different order. It would be moving faster than the speed of light in a perfect vacuum, the ultimate cosmic speed limit. Theorists predicted that a charged tachyon, should one exist, would constantly emit this Cherenkov radiation even in the vacuum of empty space. It would be perpetually bleeding energy, painting a streak of light across the cosmos. To find one, you wouldn't look for the particle itself. You would look for the light of its arrival, a flash that would appear spontaneously out of the vacuum, seemingly uncaused, a signal from a particle that had not yet reached your detector. Imagine vast cathedral-sized tanks of ultra-pure water buried deep beneath mountains to shield them from the constant rain of cosmic rays from our own sun and galaxy. Instruments like the Super Kamiokande in Japan, a colossal cylinder holding 50,000 tons of water and lined with over 13,000 golden light-sensitive eyes, called photomultiplier tubes, were built to study neutrinos. But in their spare moments between the faint ghostly flashes of neutrino interactions, they listened to the silence. They watched the darkness, waiting for a spark of Cherenkov light that had no origin, a flash that would signal the arrival of something from beyond the veil of light speed. Year after year, these subterranean sentinels stared into the abyss. They recorded the predictable flickers from known particles, the background hiss of a quantum world. Yet the anomalous acausal flash, the herald of a tachyon, never came. The silence from these deep, dark places was deafening. It was the first piece of damning evidence, the evidence of absence. The universe, it seemed, was not producing these streaks of faster-than-light energy. The direct brute force approach had failed, leaving behind only a deepening mystery and the unsettling quiet of empty data logs. If you cannot see the creature, perhaps you can find its tracks. The search shifted from direct detection to a more subtle forensic investigation. Physicists began to sift through the debris of other experiments, looking for indirect evidence for the gravitational or energetic footprint that a tachyon might leave behind as it passed. The logic was sound. If tachyons exist, they should be a part of the universe's grand energy budget. In the high-energy collisions of particle accelerators, where matter is smashed together with near-light speed violence, every reaction is a matter of meticulous accounting. The energy and momentum before the collision must precisely equal the energy and momentum after. For decades, physicists at facilities like CERN and Fermilab have scrutinized trillions of these subatomic car crashes. They searched for a specific kind of anomaly missing energy. They looked for collisions where the final tally didn't add up, where some energy seemed to have vanished without a trace. Such a deficit could, in principle, be explained by the creation of particles that escape the detector unseen. Neutrinos do this all the time, but perhaps, just perhaps, some of this missing energy was being carried away by tachyons blasting out of the interaction faster than any instrument could register their imaginary mass, leaving a subtle but real hole in the final balance sheet. The search expanded outwards from the fury of the accelerator to the gentle decay of fundamental particles. Some theories suggested that if a particle like a proton could decay into a tachyon, it would do so with a unique signature, altering the expected lifetime and decay products of that particle. Experimentalists re-examined long-known decay chains, looking for minute deviations from the standard model's predictions for any hint of a new, faster-than-light escape route for energy. They scoured the cosmos itself, analyzing the cosmic microwave background radiation, the faint afterglow of the Big Bang. Could the presence of a primordial gas of tachyons in the early universe have left a subtle imprint on the temperature fluctuations of this ancient light? Could it explain anomalies in the rotation curves of distant galaxies, a potential alternative to dark matter? Each investigation was a shot in the dark, a search for a whisper in a cosmic hurricane. And in every case, the result was the same. The books balanced. The decay rates were stubbornly normal. The cosmic microwave background held its secrets close. The universe continued to behave as if the light barrier was absolute, its laws written in indelible ink. The net was cast wider and wider, yet it always came up empty. The tachyon was a phantom that left no tracks, a ghost that cast no shadow. Skepticism, once a healthy scientific stance, began to harden into dogma. The community was losing faith. And then, on a September afternoon in 2011, the world of physics stopped breathing. A shocking announcement came from a massive experiment called OPERA, the Oscillation Project with Emulsion Tracking Apparatus. Buried deep beneath the Gran Sasso mountain in Italy, its purpose was to study a beam of neutrinos fired straight through the Earth's crust from CERN, over 730 kilometers away in Switzerland. Neutrinos are notoriously elusive, barely interacting with matter. For years, the OPERA collaboration had been meticulously timing their near-light-speed journey. The task was monstrously complex, requiring atomic clocks synchronized by GPS satellites with a precision of billionths of a second. The goal was to study how neutrinos changed from one type to another during their flight, but in the process they noticed something else, something impossible. Systematically, consistently over thousands of measurements, the neutrinos appeared to be arriving in Italy about 60 nanoseconds sooner than they should have. 60 billionths of a second. It is a sliver of time so small as to be almost meaningless in human terms, but in the realm of particle physics it was an eternity. It meant the neutrinos had traveled faster than light. The news spread through the scientific community like a shockwave. For a brief, dizzying moment, it felt as if the world had changed. Was this it? Was this the discovery that would rewrite a century of physics? Tachyons were suddenly front-page news. Old theories were dusted off, new papers were written overnight. The implications were staggering. If neutrinos, particles we knew and studied, had a tachyonic nature, then Einstein's wall had a door after all. The OPERA team, acutely aware of the magnitude of their claim, were their own harshest critics. They presented their findings not as a discovery, but as a baffling anomaly, inviting the entire world to scrutinize their work to find their mistake. For 6 months, the physics community was in a state of suspended animation. The stakes were too high for a simple mistake. Every aspect of the monumentally complex experiment was re-examined, recalibrated, and recalculated. Other experiments around the world raced to try and replicate the result. It was a period of intense collective soul-searching. Could everything we thought we knew be wrong? Was the universe stranger and faster than we had ever dared to imagine? The resolution, when it came, was not a grand scientific revolution, but a profoundly human and humbling lesson. It was not a flaw in the grand theory of relativity, but a flaw in a single physical connection. Deep within the experiment's complex timing system, a fiber optic cable, the very instrument responsible for synchronizing the master clocks, was not properly plugged in. This tiny, almost comical error, a loose connection, had introduced the 60 nanosecond delay that the scientists had mistaken for an early arrival. Once the cable was secured and the experiment was rerun, the anomaly vanished. The neutrinos, it turned out, arrived precisely on time, obeying the cosmic speed limit with perfect, unwavering fidelity. The dream was over. The excitement evaporated, replaced by a collective sigh of relief tinged with a faint sense of disappointment. The OPERA anomaly became a cautionary tale, a stark reminder of the unforgiving precision required to probe the foundations of reality and of how easy it is to be seduced by a beautiful revolutionary idea. For the search for tachyons, it was a devastating blow. The best, most tantalizing piece of evidence ever recorded had turned out to be nothing more than a loose wire. It was the final high-profile failure that seemed to close the case. The experimentalists had given it their all. They had looked, and there was nothing to see. This string of failures, culminating in the public deflation of the Opera result, marked a profound turning point. The focus of the most creative minds in theoretical physics began to shift. The question was no longer, where are tachyons, but a far more challenging and introspective one. Why times aren't times they here? If the mathematics permits their existence, why does the physical universe seem to forbid them so? Absolutely. The absence of evidence was now so overwhelming that it had become evidence of absence. This prompted a radical re-evaluation of the entire concept, pushing it from the realm of plausible discovery into a more abstract theoretical space. Physicists began to work not on proving that tachyons exist, but on formulating theories that could explain their apparent non-existence, or more subtly, could explain how they might exist in a way that renders them utterly invisible to us. It was a retreat from the laboratory back to the chalkboard, but this time the goal was different. It was an attempt to put the tachyon back in its box, to find a natural, compelling reason for the universe to enforce its speed limit. One of the most elegant and powerful ideas to emerge from this period of introspection was the concept of tachyon condensation. It proposed a radical reinterpretation of what we call empty space. What if the vacuum state we inhabit, the state of lowest possible energy, is not the true vacuum? The theory suggests that the hypothetical quantum field that would give rise to tachyons is inherently unstable. Imagine a pencil perfectly balanced on its tip. This is a state of high potential energy, a tachyonic vacuum. The slightest nudge will cause it to fall, releasing its energy, until it lies flat on the table in a new stable state of minimum energy. Tachyon condensation theory posits that our universe may have undergone a similar process in its very first moments. If a tachyon field ever existed, it would have been so unstable that it would have immediately collapsed or condensed into a new stable vacuum, the vacuum we experience today. In this new true ground state, the excitations of the field are no longer tachyons. They are normal, slower than light particles. One of the most stunning predictions of this idea is that the famous Higgs boson, the particle responsible for giving mass to other fundamental particles, might actually be the remnant of this ancient tachyon condensation. In this view, tachyons did exist, but only for an infinitesimal fraction of a second after the Big Bang. They were the architects of our vacuum, the unstable ghosts whose collapse gave birth to the stable reality we now inhabit. They are not here because their work is done. This theoretical pivot opened up other, even more exotic possibilities for how tachyons might be hidden from us. Perhaps their interactions with our world, with the particles of the Standard Model, are almost non-existent. We know that dark matter, which makes up a vast portion of the universe's mass, is all around us, passing through our bodies by the trillion every second, yet we cannot feel it because it interacts only through gravity. Perhaps tachyons are even more aloof. Their interactions could be governed by a force so incredibly weak, or mediated by particles so fantastically massive that the probability of ever detecting one in an experiment on Earth is practically zero. They would be shadow particles in the truest sense, inhabiting the same space-time as us, but belonging to a different, almost completely separate reality. They could be forming and decaying all around us, a seething foam of faster-than-light activity, but their existence would have no bearing on our own. Our universe of light, matter, and energy would be to them as transparent and untouchable as a ghost. This provides a convenient, if ultimately untestable, explanation for the great silence from our detectors. We can't find them because they are fundamentally designed not to be found. Ultimately, the inability to find any empirical footing has pushed the tachyon to the very fringes of physics, into the highly speculative and mathematical realms of quantum gravity and string theory. In these advanced frameworks, which seek to unite Einstein's relativity with the bizarre rules of quantum mechanics, tachyons sometimes appear not as physical particles, but as symptoms of a deeper instability in the theory itself. In the early days of string theory, for instance, certain versions of the theory were plagued by tachyonic solutions. These were not seen as predictions of new particles, but as mathematical red flags indicating that the theory was incomplete or fundamentally flawed. The goal became to formulate a version of string theory, a stable, consistent one that was free of these tachyonic instabilities. In this context, the tachyon is a mathematical demon that must be exorcised, a signpost pointing away from a dead-end street in the labyrinth of theoretical physics. It suggests that at the most fundamental level, the level where space-time itself becomes a quantum entity, the universe has its own internal consistency, checks its own mechanisms for preventing the paradoxes of faster-than-light travel from ever manifesting. And so the tachyon finds itself in a state of theoretical quarantine. It is a concept too compelling to discard entirely, yet too problematic to be accepted into the mainstream. It has been relegated to a wild frontier where our current understanding of physics breaks down a place where a faster-than-light particle becomes just one of many strange possibilities alongside extra dimensions vibrating, strings, and quantum foam. The downward path from hopeful search to profound skepticism has led us here to the edge of known science. The experiments have failed. The direct evidence is non-existent. The theoretical justifications have become exercises in explaining an absence. We have been forced to accept that if tachyons do exist, they are hidden from us by a veil of physics so subtle or so extreme that we may never have the means to pierce it. They have become the ultimate cosmic enigma, a creature born from our most successful theories yet seemingly banished from the very reality those theories describe. The search for tachyons has forced us to confront the limits of our own perception and to wonder what other fundamental truths about the cosmos might be lying just beyond our reach, forever locked away behind the impenetrable barrier of light. And so, after a long and exhaustive hunt across the vast cosmic plains, the verdict begins to crystallize. The search which we pursued with such relentless optimism through the static of dying stars and the fire of nascent galaxies has yielded nothing. No telltale streaks in our particle accelerators, no anomalous bursts of energy heralding a visitor from the future, no signature in the ancient light of the cosmos that screams of a particle born to break the ultimate law. The silence from the superluminal world has been absolute and unbroken, deafening emptiness that speaks with more authority than any single discovery could. In the great celestial courtroom where theories are tried by the unforgiving jury of observation, the case for the tachyon as a real physical particle has for now been dismissed. The conclusion reached by the scientific community was not born of a single dramatic refutation, but from the slow, steady accumulation of this profound absence. It is a consensus built not on a closed door, but on 1,000 unopened ones. For every avenue of investigation we explored, for every clever trap we laid for these fleeting phantoms, we found only the familiar, stubborn physics of our light-bound universe staring back at us. The overwhelming weight of evidence, paradoxically, is a lack of evidence. When you search for a monster in every shadow and find none, you must eventually consider the unsettling possibility that the monster lives only in the mind. This conclusion is cemented by the colossal theoretical hurdles that never truly went away, chief among them the spectre that has haunted our journey from the very beginning: causality. The tachyonic anti-telephone, that elegant and terrifying thought experiment, remains a fatal flaw in the particle's resume. The idea that we could send a message that arrives before it is sent doesn't just bend the rules of physics, it shatters the logical foundation of reality itself. It breaks the sacred arrow of time, the fundamental principle that effect must always follow cause. A universe where a window could shatter before a stone is thrown, where a star could die before it is born, is not just a strange universe. It is an incoherent one, a cosmos that cannot logically exist. Physicists, for all their comfort with the bizarre and the counterintuitive, hold the principle of causality as sacrosanct. It is the bedrock upon which all of science is built, the operating system of the cosmos that ensures a comprehensible ordered existence. To allow for true tachyonic particles would be to introduce a fatal paradox, a glitch in the source code of the universe from which it could never recover. Without extraordinary world-altering evidence to the contrary, the community has had to conclude that the universe protects its own logical integrity. The speed of light, it seems, is not merely a cosmic speed limit. It is a firewall, a barrier, erected by nature itself to protect the past from the future, to keep the timeline of reality from unraveling into an impossible knot of contradictions. The universe, it would appear, does not play dice with its own history. Yet, to declare the tachyon a failure, to label it a mere mistake, and cast it onto the ash heap of abandoned ideas would be to fundamentally misunderstand its monumental importance. This is the crucial twist in our story. The tachyon's greatest contribution to science was not in its potential existence, but in its profound and beautiful impossibility. It was a ghost that forced us to map the boundaries of the real world with unprecedented precision. By chasing this phantom, we didn't find a new particle, but we gained a far deeper, more intimate understanding of the universe we already inhabit. The tachyon in its death became one of the most powerful thought experiments in the history of physics, a theoretical tool that has shaped our modern understanding of existence in ways its creators could have never imagined. Its first great legacy was in cementing the very theory that gave it birth, Einstein's special relativity. By pushing the equations to their absolute breaking point, by exploring the strange inverted world on the other side of the light barrier, physicists were forced to confront the deep and unshakable truth of Einstein's vision. The tachyon became the ultimate stress test. Its paradoxical nature, its violation of causality, its bizarre energy profile served only to highlight the perfect, self-consistent elegance of a universe where nothing with real, ordinary mass can ever reach the speed of light. The light barrier isn't an arbitrary rule. The very weirdness of the tachyon proved that it is a fundamental feature of space-time's geometry. It is the horizon of the conventional. In a strange way, the most compelling argument for why the speed of light is the universal limit is the sheer reality-breaking chaos that ensues the moment you pretend it isn't. But the story does not end there. The idea of the tachyon, this concept of something with an imaginary mass, refused to simply vanish. Instead, like a seed planted in fertile soil, it found a new, more profound and startlingly real home in the esoteric world of quantum field theory. Here, in the mathematics that describes the fundamental forces and particles of our universe, the ghost of the tachyon reappeared. But this time, it wasn't a particle, it was a message. In the language of quantum fields, a tachyonic field or a tachyonic mode does not represent a faster-than-light entity. Instead, it is a mathematical signpost, a cosmic red flag signaling that the system you are describing is profoundly unstable. Imagine a pencil balanced perfectly on its sharpened tip. That state of perfect, precarious balance is a state of high potential energy. It is symmetric, but it is deeply unstable. The slightest perturbation, a breath of wind, a subtle vibration will cause it to fall. It wants to collapse into a more stable, lower energy state lying on its side. In the language of physics, that perfectly balanced, unstable state is tachyonic. The imaginary mass that appears in the equations is not describing a real particle's mass. It is a mathematical symptom of this instability, a sign that the field is sitting at a peak of potential energy, a false vacuum, and is destined to roll down into a valley, the true vacuum, releasing energy as it does. This concept, known as tachyonic condensation, is not some abstract theoretical curiosity. It is one of the most important discoveries in modern physics. It is the key to understanding how our universe came to be the way it is. And its most spectacular application is in explaining the origin of mass itself. We must travel back in time to the first searing moments after the Big Bang. The universe was an incandescent soup of energy and massless particles, a place of perfect symmetry. In this primordial state, the fundamental forces of nature, like electromagnetism and the weak nuclear force, were unified, indistinguishable from one another. Every particle moved at the speed of light, unencumbered by mass. Governing this inferno was a quantum field that permeates all of space, a field we now call the Higgs field, and in that early symmetric universe, the Higgs field was in an unstable state. It was balanced on that metaphorical pencil tip. Its own equations revealed a tachyonic quality. It was a field primed to collapse, and a mere fraction of a second after the beginning of time, as the universe expanded and cooled it, did exactly that. The Higgs field underwent a phase transition, a moment of tachyonic condensation. It fell from its high-energy symmetric state into the stable lower-energy state that fills our cosmos today. The consequences of this single event were nothing short of reality-defining. As the field condensed, it shattered the perfect symmetry of the early universe. It differentiated the electromagnetic and weak forces, giving them the unique characteristics we observe today. But most importantly, it filled space-time with a kind of cosmic molasses. As once massless particles moved through this newly settled Higgs field, they began to interact with it, to drag against it. This interaction, this resistance to motion, is what we perceive as mass. The electron, the quarks that form protons and neutrons, the heavy bosons that carry the weak force, they all acquired their mass from this primordial fall. The very substance of you, the solidity of the world beneath your feet, the inertia that governs the motion of galaxies, was born from a tachyonic instability at the dawn of time. So the ultimate irony is this: the faster-than-light particle we search for in vain may not exist, but the mathematical ghost it left behind is the architect of our physical reality. The tachyon, the hypothetical breaker of cosmic law, found its true purpose as a catalyst for cosmic creation. It is not a particle that travels through space, but an instability that transformed space itself, turning a massless symmetric inferno into the complex, massive and structured universe we call home. The idea that began as a playful footnote to Einstein's relativity became the central mechanism for explaining our own existence. It is a stunning testament to how even our wrong ideas, our most audacious theoretical leaps, can lead us towards a deeper truth. This pattern repeats itself across the frontiers of theoretical physics. In the early days of string theory, the ambitious attempt to unify all the forces of nature into a single framework, tachyons, appeared again. The initial mathematical models were plagued by tachyonic modes, which, just like in quantum field theory, signaled a fundamental instability in the theory itself. These were not predictions of faster-than-light particles, but rather mathematical error messages telling physicists that their model of reality was incomplete, that it was balanced on a knife's edge and needed to be refined. The quest to eliminate these tachyonic instabilities was a primary driving force that led to the development of more sophisticated and stable versions of the theory, like the various superstring theories. The tachyon once again played the role of the gadfly, the persistent problem that forced theorists to dig deeper, to refine their assumptions, and to build more robust and elegant models of the universe. It became a kind of cosmic whetstone, an object against which the blade of theoretical physics could be sharpened. By demanding a universe free of its causal paradoxes, physicists were forced to build theories that were not just predictive, but logically sound and self-consistent. The tachyon, in its role as the ultimate saboteur of logic, became the guardian of it. It patrols the boundaries of sensible theories, and its appearance in an equation is a clear warning. Here, be dragons. Your understanding of nature is flawed. Go back and think again. It is a beautiful recursive piece of logic. The very thing that threatens to make the universe nonsensical has become an essential tool for making sense of it. And this brings us to its final, most enduring legacy, the philosophical one. The tachyon forces us to stare into the abyss of our own assumptions. Why do we find the idea so compelling, so seductive? It is because it speaks to a deep, primal human desire to transcend limitations, to break the shackles of our own cosmic prison. The speed of light represents the ultimate boundary, the wall of the cosmic cage in which humanity is confined. The tachyon was the dream of a key, a secret passage through that wall. And even if that key has proven to be a fiction, the act of dreaming it, of conceptualizing it, has permanently expanded the horizons of our imagination. It compels us to ask the deepest questions. Is causality truly fundamental, or is it an emergent property of our particular phase of the universe? Could there be domains of reality perhaps beyond our observable horizon, or in other dimensions where the rules are different? By contemplating the tachyon, we are not just contemplating a particle, we are contemplating the very nature of physical law. Are the laws of our universe the only possible laws, or are they just one set of rules in a vast multiverse of possibilities? The tachyon is a mirror reflecting the limits of our own knowledge. Its shadowy form, always just beyond the reach of our experiments, reminds us that our understanding of the universe is a work in progress, an island of knowledge in a vast ocean of mystery. It has taught us that the most fruitful questions in science are often the ones that lead to a no. The search was not a waste. Every failed experiment, every null result was a new piece of the puzzle, a confirmation of the strength and resilience of the theories we already have. We did not find the tachyon, but in the process we found a new and profound respect for the cosmic order, for the intricate, beautiful, and consistent set of rules that govern our existence. We learned that the universe is not just strange, but that it is coherent in its strangeness. The tale of the tachyon is therefore a cautionary one, but also a deeply inspiring one. It warns us of the allure of ideas that are elegant in theory but absent in reality. Yet it also celebrates the power of human imagination to push beyond the known, to ask what if, with such rigor and sincerity that the asking itself transforms our understanding. The particle may be a ghost, a spectre haunting the equations of relativity, but the questions it raised are very much alive. They continue to animate the search for new physics, driving us to reconsider the nature of space, of time, and of information itself. And so we close one chapter of our quest. The direct head-on assault on the light barrier embodied by the tachyon appears to have reached its end. Nature, it seems, has chosen to protect its causal structure with a ferocity that permits no exception for a simple point-like particle. But the dream it ignited, the dream of the stars of instantaneous travel, of transcending the immense isolating distances of the cosmos, that dream has not died. It has simply been forced to become more clever, more subtle. If we cannot break the light barrier, perhaps we can cheat it. If a straight line is forbidden, perhaps we can find a way to bend the universe itself to find a shortcut. The ghost of the tachyon, having shown us the front door is locked now, invites us to look for other passages, other, more exotic pathways through the very fabric of space-time. And so, after our long and frantic chase, the ghost recedes. The superluminal phantom, which promised a revolution, which offered us a glimpse into the forbidden realms of time, slips back into the theoretical ether from which it was born. Our detectors fall silent. Our telescopes, sweeping the cosmic voids for its telltale signature, find only the steady, familiar light of a universe that appears in the end to obey its own most sacred law. There is no crescendo of discovery, no Nobel Prize, no triumphant press conference announcing the dawn of a new age. There is only the quiet, profound, and deeply resonant conclusion that the universe as we understand it holds firm. The wall of light, that ultimate speed limit defined by Einstein, remains unbreached. It would be easy then to close this chapter and call it a failure, to label the tachyon a beautiful but flawed idea, a mathematical curiosity that led us on a grand cosmic wild goose chase. But to do so would be to miss the entire point of the journey. It would be like exploring a vast, uncharted continent, only to lament that you did not find the fabled city of gold, ignoring the rivers you mapped, the mountains you scaled, and the new understanding of the world you gained along the tachyon. You see, was never just about a particle. It was a question posed in the language of mathematics. A question so fundamental, so audacious, it forced us to place our most cherished physical theories into an intellectual crucible and turn up the heat. For decades, special relativity had been the bedrock of physics, a powerful and elegant description of space, time, and motion. Yet, like any great pillar of knowledge, it needed to be tested not just at its foundations, but at its most extreme and improbable frontiers. The tachyon was the ultimate stress test. It was a theoretical sledgehammer, swung directly at that pillar, designed to see if any cracks would appear. By imagining a world where particles could outrun a photon, physicists were not trying to tear Einstein's theory down. They were trying to understand its true strength, to trace its load-bearing beams and find its absolute limits. They were asking, what happens if we break the one rule that seems utterly unbreakable? Does the entire edifice of modern physics collapse into meaningless chaos, or does it reveal a hidden architecture, a deeper, stranger reality? In confronting this question, we were forced to look causality squarely in the face. Before the tachyon paradox, causality was something we took for granted, the intuitive, unspoken rhythm of existence. An acorn falls before the oak tree grows. The lightning flashes before the thunder rolls. It is the fundamental syntax of reality, the arrow of time that gives our lives meaning, order, and consequence. But the tachyon threatened to snap that arrow in two. The spectre of receiving a message before it was sent, of seeing the effect before its cause, was more than just a quirky logical puzzle. It was an existential threat to the very notion of a coherent universe. If the past could be altered, if the future could influence the present, then the logical chain of events that underpins all of science, all of history, all of our experience would dissolve. The search for the tachyon, therefore, became a defense of causality itself. Every experiment designed to detect its faster-than-light signature, from the timing of cosmic rays to the decay of subatomic particles, was in its essence an affirmation of a comprehensible reality. With every null result, with every experiment that came up empty, we were not met with disappointment, but with a growing sense of relief. We were discovering with ever-increasing precision that the universe does not play dice with the flow of time. We learned that causality is not merely a philosophical preference or a byproduct of our particular biological perception. It appears to be a non-negotiable fundamental law of the cosmos, as integral to its structure as gravity or the charge of an electron. This profound understanding, this elevation of causality from an assumption to a rigorously tested principle, is one of the tachyon's greatest and most ironic gifts to us. The particle that threatened to destroy our concept of time ended up becoming its most powerful defender. This entire saga stands as a perfect incandescent example of the scientific method in its purest form. It begins with a bold, almost heretical what if. What if something could exist in that forbidden realm beyond light speed? This hypothesis, born from the elegant symmetries of an equation, is not dismissed out of hand. Instead, it is embraced, explored, and its consequences are followed with ruthless intellectual honesty, no matter how bizarre they seem. Theorists build worlds around it, imagining how such a particle would behave, how it would interact, what its footprint would be on the tapestry of space-time. They don't shy away from the paradoxes. They dive into them, using them as tools to refine the hypothesis. Perhaps tachyons power quasars. Perhaps they are the messengers of a hidden sector of the universe. Perhaps they are the key to quantum gravity. Then the experimentalists take over. They become the ultimate arbiters, translating abstract theory into tangible real-world quests. They design detectors of breathtaking sensitivity, sifting through petabytes of data from particle accelerators, staring into the deepest reaches of the cosmos, hunting for a whisper, a flicker, a shadow that isn't supposed to be there. This is where imagination meets the unforgiving rigor of reality. The process is slow, meticulous, and often frustrating. Years, even decades, can be spent chasing phantoms in the data, eliminating sources of noise and refining the search. And when after all that effort the result is null, it is not a defeat, it is a discovery. A null result is a piece of knowledge, a new boundary drawn on the map of what is possible. It tells us with quantifiable certainty, the thing you are looking for is not here in this way under these conditions. Each failed search for the tachyon didn't close a door, it simply built the walls of our current understanding a little higher, making the structure stronger and more robust than it was before. The intellectual framework developed to hunt for this one hypothetical particle has had echoes throughout the landscape of modern physics. The very techniques and theoretical tools forged in the quest for the tachyon are now being repurposed in our search for other equally elusive entities. When physicists hunt for the ghostly particles of dark matter which pass through us by the trillion every second without a trace, they are using the same logic of looking for subtle indirect effects that was honed during the tachyon searches of the late 20th century. When they puzzle over the strange accelerating expansion of the universe, driven by a mysterious dark energy, they are once again confronted with a phenomenon that challenges our deepest intuitions about the cosmos, much as the tachyon did. The ghost of the faster-than-light particle taught us how to think about the unthinkable, how to design experiments to catch the uncatchable, and how to interpret silence not as absence of evidence, but as evidence of absence within specific, well-defined limits. It was a training ground for the scientific mind, preparing us for the even greater mysteries that lay ahead. And what of the human element in this grand story? It is a tale of brilliant, daring, and sometimes eccentric minds. From the foundational insights of Arnold Sommerfeld and George Sudarshan to the popular imagination fired by science fiction authors, the tachyon represents our innate desire to push against boundaries, to dream of transcending our own limitations. It speaks to the part of us that looks at a wall and doesn't just see an obstacle but wonders what's on the other side. It is a story of countless graduate students spending sleepless nights calibrating detectors of theorists, scribbling on chalkboards, arguing passionately over the fine print of the universe's cosmic contract. This is not a cold, dispassionate process of crunching numbers. It is a profoundly human endeavor driven by curiosity, fueled by collaboration, and guided by an unwavering commitment to follow the evidence wherever it may lead. Even when it leads, as it has so far, to a dead end. So we are left here at the edge of the speed of light, staring out into an immense and silent cosmos. The tachyon remains a creature of pure theory, a celestial mirage. It is a ghost in the machine of physics, a what-if that served its purpose as an intellectual whetstone, sharpening our understanding of the world we actually inhabit. It forced us to choose between the tantalizing possibility of faster-than-light travel and the logical coherence of a universe where time flows in one direction. And the universe, it seems, has made its choice. But the story doesn't truly end here, because the questions never do. By proving the tachyon to be a fiction, we have not shrunken the universe. We have simply clarified the rules of the game. We now understand the landscape of reality. With a little more clarity, the map of the possible is a little more detailed. The areas marked here be dragons are just as important as the charted territories, for they define the scope of our knowledge and hint at where the next great discoveries might lie. Perhaps one day a new theory will emerge, a deeper theory of quantum gravity, or a unified field theory that provides a loophole we cannot currently conceive of. Perhaps it will show that our understanding of causality itself is incomplete, an approximation of a more complex, multi-layered reality. The universe is under no obligation to conform to our expectations, and its capacity for surprise is seemingly infinite. The legacy of the tachyon is not the particle itself, but the spirit of inquiry it represents. It is a testament to the power of a speculative idea to galvanize decades of research and deepen our appreciation for the subtle, elegant, and inviolable laws that govern our existence. So, as you look up at the night sky, at the ancient steady light from galaxies that has traveled for billions of years to reach you, traveling always at that one unbreakable cosmic speed, remember the phantom that we chased among those stars. Remember the particle born of mathematics that taught us so much about the nature of reality precisely because it does not seem to exist. It reminds us that science is not just a collection of facts, but a dynamic, ongoing process of questioning, challenging, and exploring the very limits of imagination. It is a journey, not a destination. And on that journey, even the ghosts we meet along the way can be our greatest teachers, pointing us toward a more profound truth, and reminding us always that the most beautiful mysteries are the ones that still await us hidden just beyond the reach of our current understanding, waiting for the next bold question to be asked. The universe is vast, and our exploration of it has only just begun.